another framework to accelerate system validation on emulation. Abstract. This paper discusses about the traditional approach used in emulators to use runtime features like trigger, dump, force, monitor, and dump load memory. So the pitfalls of using traditional approach, this paper then proposes another framework to use the runtime features of the emulator and control it with the software running on the DUT itself. The novel approach creates an abstraction of underlying the emulation hardware for software user who is validating his SoC, which is ported to the emulator. Keywords: emulate, DPI, transactor, validation, acceleration. Introduction. The semiconductor industry is growing exponentially, which keeps increasing design complexity of SoC. It's big challenge for industry to validate its chip on time and stay in competition to the market. Simulation verification of SoC is time consuming, so most of the SoC level test scenarios are moved from the simulation to emulation to accelerate verification. With each SoC cycles, as more test cases and scenario and run on emulation as compared to simulation. With this comes the requirement to have framework for the emulation platform so that the test cases can be ported onto emulator seamlessly and in a user-friendly manner. Simulator has a framework which has a common system value tasks which does the trigger down, and force release and read write to a memory. To get signal values, etc. from DUT or testbench benches. Emulator does not have these features to be used from DUT directly. These features are only available at runtime using commands or software functions from testbench. There is no way to control them from the emulator hardware while the DUT is running. This paper discusses on this problem and another approach to overcome it. Section 2. Traditional approach. Traditional approach to use these runtime features on emulator were through commands provided as part of the library, but these commands need manual intervention and can be controlled through software, and it is also not as close to the simulation framework. For example, if a user wants to start the dump before a failing function in C code running in his design under test and stop it once the function execution complete. This is to be done on emulator. We need to either call the API from the C test bench onto the emulator or using runtime commands which are part of the emulation framework. So there is no way we can control this from the emulator. In addition, user needs to find extract signal which he can trigger when the function is executed, or the timestamp at which the function executed to take a dump on emulation hardware. One more example where the user is limited on emulation side is to model PLL so he can generate all possible frequencies. The simulation models cannot be directly ported as synthesizable code to emulator, so this limits the number of scenarios which can be run on the emulation, unlike a simulation. So, A dump example. Let's say you have a function running in the software which you need to debug and take a waveform dump. Traditional approach is to find out the program counter or failing function and put a trigger on it in the run script and run for X amount of time. Or find out the timestamp when the function gets executed. Run for that time in the run script and then start and stop the dump. For example, if we want to take a dump when the cmd underscore initialize is executed and stop the dump once it is executed. We need to find the address of this function in the memory and trigger on the processor program counter, and then we take the dump for some amount of time. Figure 1, dump example 2 take waveform for function cmd underscore initialize. Below are the things we usually need to take care in order to take the dump for function under debug. Find out the hierarchy of a signal he wants to trigger on. So get the timestamp at which the command is executed. Get the runtime for which the cmd underscore initialize function executed, and stop the trigger based on the function execution completion. Force example. Let's say a user wants to force a signal just before the function cmd underscore initialize. So after reset underscore config, traditional approach to use the keep-on expression when the runtime reaches the function stop and force the signal and run again. Figure 2 is a force example to force the signal before function cmd underscore initialize. Pitfalls. Again, the user needs to take care of the below. Find out the hierarchy of a signal where he can trigger for function reset underscore config completion. Stop the run once the trigger point is hit. For the signal he wants to force. Run again for after forcing the signal. 3. Novel approach. We need a framework where the emulator users can control the runtime features like trigger dump, force release, and read-write memory, and change frequency, output of PLL, and etc. from the software running in duty and at runtime. Emulator has a transistor-based framework which can be an advantage to achieve a more novel approach to control runtime features of the hardware and accelerate the validation. In this framework, which we implemented whenever a register write from a CPU in the design under test happens, a DPI call is triggered from the hardware side of the emulator, which then enables the runtime features on the emulator using C++ API. For example, as discussed above, we can control the dump using a cdump function. Whenever this function is called, the software running on the CPU will write the predefined address of a system function register, which already exists in the duty. Now this generates a transition at the AXI boundary of the block where the system function register is being implemented. Once this happens, the address, data, and valid signals of the transition are extracted and fed to a bus functional model. This bus functional model converts these signals to a DPI transition using import and export commands supported by emulator. This then triggers the dump on and off API function calls of the software hardware using the library provided. This way, user can control the dump behavior of emulator without having need to call any command or function in test bench. User can control it from the software running in DUT. The figure 1 gives the top-level implementation we have used in this novel framework. Figure 3, a novel framework to accelerate system validation on emulation. So, another example which we discussed in the start is that of a PLL. We design hardware PLL such that it supports running long-time changing of PLL frequency. It includes a PLL emulation model, which enables DFS operation with the DPI-C interface in C environment. And based on the input frequency and multiplier and divider values, output frequency is calculated by the C test bench functions. The calculated output frequency is further divided based on the requirements and supplied to the respective clock wires at runtime. This frequency division helps in optimizing the frequency requirement and help user dynamically shift the frequency similar to the flexibility which the user has in simulations. User can also now test the dynamic frequency scaling DFS feature. In dynamic frequency scaling, the frequency of a microprocessor can be automatically adjusted depending on the actual needs to conserve power. So below is the sequence of 4 steps which takes place from DUT, software, C code, and emulator runtime. So a register write from CPU in the DUT is initiated based on runtime C function software wants to control. 2. Pass functional model then extract data at the AXI boundary from this register write. 3. After this, based on the extracted data or DPI, core is triggered from the hardware side of emulator to PC side. Therefore, this then enables the runtime feature on the emulator using C++ API. This is as per the runtime feature step 1 originally initiated. Figure 4. Sequence of steps in novel framework to accelerate system validation on emulation. Step 1. CPU writes to a register. In these steps, the CPU writes to a register based on a function which the user intends to execute. The unique address and the data is mapped based on the user function. Step 2. AXI extraction in BFM. In this step, based on the trigger in the register, write the CPU does, the address and data are extracted from the AXI bus. This bus is the same bus on which the CPU has initiated a write transaction. So, step 3. DPI call from a hardware to test bench. In this step, based on the extracted data messages are sent from hardware to DUT and using standard DPI call provided by emulation tool. Step 4. Runtime feature controlling using a C++ API. In this step, based on the message received in the test bench, a C++ API is called and the corresponding runtime feature of the emulator is triggered. Dump example. Let's now consider the dump example discussed in the traditional approach. Section 2. User can now have a function Let's say start underscore dump function and a stop underscore dump function before and after the function which is under debug. A user can also specify the dump underscore time function and then do start underscore dump function also. This way user can exactly take it down for the time where user wants to debug the function. These functions to start and stop is dump are written with the four steps approach discussed in the above novel framework. Section 3. Figure 5. Novel approach takes waveform dump for function cmd underscore initialize. With this approach, the user need not care about below mentioned things when running his software. User needs not be aware of hierarchy of signals to trigger the runtime for which the function takes. The time step on emulator hardware runtime when the function is executed. The stopping the emulator run manually. B. Fourth example. Now let's consider the fourth example discussed in traditional approach. Section 2. The user can now have a function, let's say force underscore signal function to force any signal at runtime. These functions to force a signal at runtime is written with the four steps approach discussed in the novel framework. Section 3. Figure 6. Novel approaches to force a signal. With this approach, the user needs not care about below mentioned things before forcing. So the user need not be aware of a hierarchy of a signal to trigger the timestamp on the emulator hardware runtime when the function is executed, stopping the emulator run manually and forcing the signal. C. Parallel example. Traditional approach to change the clock frequency of a clock and emulator was through commands provided as part of the library. But these commands need manual intervention and cannot be controlled through registers programmed in the DOT to configure the PLL. Earlier, we used to assign and force PLL frequencies before start of the emulation design run, and any subsequent change in the frequencies needs a rerun. We need a framework where the emulator users can control the PLL frequencies using register configuration, just like in Silicon. Emulator has a trajectory-based framework which can be leveraged to achieve a more novel approach to control the frequencies at the output of the PLL. In this framework, which we have implemented, whatever a register write from CPU and the design under test happens to configure the clock frequency of a PLL. A DPI core is triggered from the hardware side of emulator. This DPI core holds the multiplier and divider values of the PLL based on which clock frequency output of a PLL is decided. This DPI core then enables the runtime feature on the emulator using C++ API. For example, whenever a divider value of a PLL is changed, the divider value signal of a transaction are extracted and fed to a bus functional model. This bus functional model convert these signals to a DPI transaction using import and export command supported by Emulator. The output frequency of a PLL is calculated using this multiplier and divider values in the testbench-side. Then, this then in turn triggered the clock frequency configuration API function calls of the hardware using the libraries provided. This way, the user can emulate the PLL behaviors on the emulator without a need to call any command or function in this test bench. User can control it from the software running duty. So with this approach, now user can run scenarios where he has to change the frequency of different PLL and validate different clock ratio. User can validate dynamic frequency scaling feature of the SoC. So figure 7, novel approach to validate dynamic frequency scaling feature of SoC. Section 4, applications and limitations. This emulation framework is particularly useful to validation users who can now control the emulation hardware from the software running on the duty itself. Users can use this framework to perform below runtime features of the emulation from software itself. Triggering dump, dynamic frequency shift, dump and load memory, force and monitor signals, generate system level event. This emulation framework comes with below limitations. In some scenarios, as the functions cause delays in execution, it can impact the functionality if there is a dependency on delays caused by DPI cores. The runtime performance of the emulator may be impacted because of DPI cores. So, 5 is a preliminary result. For dynamic frequency with the scenarios, we have observed approximately x80 improvement in emulation time as compared to simulation. This helps faster verification of SoC. Below are the snippets of the result for running dynamic frequency shift scenarios run on emulator as compared to simulator. No caption for figure. Section 5 is conclusion. This emulation framework is particularly useful to validation users who can now control the emulation hardware from the software running on the duty itself. Users can debug their code by easily keeping trigger from the software itself. With this framework, they can dynamically control the frequency as in silicon by programming in PLL register and validate broader frequency ranging. This framework enables to get access to memory and signals, the 4 signals in the DOT from software, and reducing validation turnaround time. So, acknowledged references. Okay. Today, I read this paper, another framework to accelerate simulation validation on emulation. Thank you for your time and see you next time.